That won't work in the debugger. Oh, that's strange. This looks like I would be constructing an algorithm event data with just event type. Surely I did pass more than that. Then again, maybe I didn't. So now I have to find out where I did that, either with git diff or just run it in the debugger. That's a trigger somewhere. And we can't find it back. Oh, there it is, the top. Yeah, this is indeed only the type is being passed, so it's not correct then. I need to pass the sample and the label. What is the sample? The sample must be the sample that is stored in the extreme. So we pass here history current, but it might be not have a long enough lifetime. However, we're making a copy here, I think. So this is the second argument of whatever is stored in extremes. Local extreme. Second argument, no, would be the first argument. Should be the first argument. I mean, I'm looking for a sample. So I have to call this on that local extreme. In a label. Yeah. Suppose I should still use the history index. That one. I see, man. Cool. You had no troubles installing Arch. It's normally a bit of a difficulty, so of a difficult distribution to install as your first Linux. So yeah, here I have another trigger which uses this. Maybe I should just use the same thing. But then we have to call the accessor of total number of samples. And hello, how the hell do I pronounce that? Behavin? And how to? Total number of samples. Call that on his history. History. I don't see. Oh, he has an history. You see the problem that I had, the annoyance that I had, is that at the moment when a local extreme is being, oops, we even crashed, sorry. Yeah, okay, I'm in the middle. I mean, so let's say we find this local extreme here, then I had a cross there permanently, so I just know that what all the local extremes, maybe I should even give them another color, like these things are black. Maybe I should add a red something, and that should just stay. No, well, it was not there, so that's what I'm adding now. So that is received here, and then I can actually plot it. And of course it's going to be a lot like the history thing. Plot samples, data index, initialize. Create point and create text. The hell is plot samples? This is literally an a point and a label per history index, but the history rotates, so these things get reused. The history index. I need a different one, and this one can grow out of bounds, so we need a vector. I'm just going to use this standard vector with something. Plot. Yeah, whatever. Local extremes. The thing needs a name. And that must contain, yeah, also a point and a text thing. I could use plot symbol actually. Yeah, let's just reuse this thing. Storing plot samples in it as well. Vector means that the plot samples will be moved in memory at arbitrary moments. I'm not even sure if we can move a plot point without problems. That would be this one. Well, that doesn't look like a problem, except of course that both point and draggable are moved in. Well, if it is a problem, I just should not compile, of course. No, that's not a problem. I'm gonna assume it's not a problem. Pointer to the master. Oh, right. Okay. And then created point and label. So this was my vector now. The plot local extremes is the vector, and plays back then adds a plot sample which must start with a pointer to something. We probably have to begin with something like this also. I get to my data. The data was a new local extreme data. With a local extreme I need to make accessors apparently. It's kind of like this, right? So we just call this local extreme const return local extreme, semicolon, and the other one is like this to access the label. Still only two. Bit stupid names, but I'm getting impatient. Data dot local extreme, and that returns a reference, and this thing wants a pointer, so just make a pointer in. And then we had to pass the label. That was it. Why would I pass the label? Of course I don't want to pass the label. No label. This. Create a point. create a point layer. I guess that works. Plot point style. So I want to change the point style. Data current W value, which is now the accessor to the local extreme. That's just this call again, I think. Yep, it's like the x and the y coordinate of the point. Comma, and then the text. So plot create text, layer, level style. Why not all the same? Could put it above maybe, in order not to go through the history levels. And then we need to create the same point. It's going to be this. And then the label. One more. Okay, what am I missing here? I wanted to change style. Of course, I forgot how to do that, but probably I just passed something which is created from initializer list, and I wanted to change the color, which I should be able to do something like this. I mean, this is like the way you would want it to work, and therefore it will work like that, right? I mean, otherwise the design was not good. Well, it's the same as this. Yeah. Yep. And now maybe put it centered above or something. I'm not sure about that though. I could do that. There goes this. No matching function for call to object of type point style. Candidate function not viable. Cannot convert initialize list argument to point base style params delta. Yeah, it's always very hard to find back. Probably I should look here. Point style params default looks like this is. Oh, I have to set a color index. Snore. Can't set a color. That's annoying. Keeps being hyper annoying. What was it? Here. Of course, we have absolutely no clue what index is what color. I use a lot of indexes. There must be a table somewhere where I can see which index is what. And I have no idea why I stored that table. Nope. Well, that is a good guess. Color.cxx. There it is. And what looks like red to me, I wanted to make it red. Really? No red? How the hell? Oh, here's a red one. Well, reddish. This is 0, 13 down. It's that one. So it would be 14. Brighter than this one. Let's try 14. I have no clue. Now, of course, you don't know what I was editing. This maybe. I'm going to try 14. I think it became blue. Yeah, anything but red. So these are red. Now suddenly these are red. And this one is blue. Well, at least it's a different color. Gee. I thought I had black these things before. So weird. Okay, these are red. Yeah. Okay, I think it works. Maybe RGB, maybe make it green. Try green. Does anyone see green? This is dark green. Oh, maybe I'm using the I should be using the white background color. That's the reason. So we go here to number 14. That's not really red, is it? Nothing green, you know. The idea of this table is that you just let the thing figure it out. So you just take the first one and then the next, and they should all have a different color. But no, I want to pick my own color, so yeah, then the whole table is a bit stupid to use actually. I want to use this when I have an arbitrary number of data points. So like 10 data points, 15 different data points. Then you don't want to have to type in 15 different colors. Then it should be automated. Anyway, I'm going to use this one, 0, 1, 2. Let's do 2 super green. And I don't know where I was editing. Here. I think 2 is gonna work. Now I want green anyway. Yeah, super green. And another green one. And another green one. Good. Now, let's see where we stop now. It stops when you go back here. Okay, so this is my current problem that I need help with. I'm not gonna get any help here because everyone left. Look. I think this drop here should tell me that something went wrong. And then I think that means that I have to jump here and forget about this one. So it should make a fit. The next fit after this one should be between this point and that one, not between this point and that one. And the reason is that this is so far off. Now this one is also far off. So that even the fit between this one and that one then should result in a maximum, after which we want to have a cubic fit between that maximum and still number 14. And that's what I have to implement. Hey. How do you call that? Shear track, jump, I guess. So, you can hear me, Arconis? That is... It's live now for you. Okay, man, cool. Well, I want to show you something shortly, because I have to go to bed. So currently I'm having... I got rid of the tests with the gradient descent.cxx is no more. All those 4, I think, tests have been now moved to the gradient descent test suite. And this is a new file actually that is not working at all. So if you run the gradient descent to test suite at the moment, well, I have to commit what I have, I guess. Still, you get this one, and there's a pretty interesting thing going on here. It has a bit of a startup. The first 13 points you can just skip over. So we just start here and then it goes to the right, because yeah, that's downhill, yeah. And then it fits a cubic through the last 2 points. Every time you have 2 points, you can fit a cubic, okay? We are going to the right. We're going to a minimum, so the cubic says the minimum is here. So the next sample is going to be taken here, okay? And then it draws the next cubic through the new point and then number 1. So it's just every time the last 2. So now we have this cubic, and then we do it again. We jump to the minimum of this cubic. So that would be somewhere here. And now we have this cubic, because now it's fitting through 2 and 3, which are very close. And of course, this cubic is a really good fit for this minimum here. So if we jump again, then we really find that we're hardly moving and we know that we found the minimum. So now the minimum is found, it is now colored in green. At that point, we fit a 4th degree polynomial through 3 points. So we had 2 points here already, and it just finds the nearest 3rd point, which is necessary to fit the not cubic by a 4th degree polynomial. So that's even a better fit, and that one has then, because this is a minimum, it has an extreme on the left and the right, both maximum. And based on that, it decides which way to go. And the funny thing is, even though this point is of course filled deeper than the points on the right, it still decides to go to the right, because it can only choose between this maximum, and it goes to the lowest one. So this maximum here is lower than that one, yeah, for this fit. Therefore we jump here. Now we have the cubic that goes through 4, which is the in the local extreme here, the minimum, and 5. And we are still going to the right. And since we were in a minimum, we are looking for a maximum again. So it's going to jump here. And then we have a fit through 5 and 6, and it's going to jump here. Yep, sell the maximum. And you get the repeat of this, that the points get closer and closer until we really find the maximum here. And then it's doing the same thing. It fits a 4th degree polynomial. and decides which way to go. No, it does not decide which way to go. We were going right, so it keeps going right. So it ignores that this fact. This one is lower, but yeah, we already were there. We're just going to that one because that's on the right. Now we fit the cubic again through 8 and 9. And we're looking for a minimum now, so now it's jumping here. And then again through 9 and 10, and we minimum there, blip, until we find this minimum as well, which is now, I guess. Now it sees that this minimum is not as deep as this one. Yeah, so we have a minimum here, then we have a maximum, and then we have a minimum that is not as deep, as low as this one. And that's the reason to stop. Yeah, I continue from minimum to minimum to minimum as long as they go deeper. So this one now stops. Now we want to go back. Now I'm going to go left from the deepest one, which is here. And we should find this point and then this point and then continue, because this one is lower than that one. So then we found that one and then that one. And this is lower than that one, therefore we continue. So we find that one and then the next one and so on. So if this would grow in amplitude infinitely, we would infinitely go to the left here. Okay, how is this going? Well, we should fit, no, we jump here, sorry. And then I add the scale that belongs to this fit, which is probably this distance. Well, it's still 13. Okay, there it is. Okay, so a little bit less. So this is just the scale, you know, the scale over which things change. So I think it's a very reasonable jump from there to there. It's not like 1/1,000,000th or all the way here. Yeah, it's a really nice jump. So now we have a fit through 4 and 14 cubic all the time. And we were in a minimum, and now we want to go left looking for a maximum. However, and now it starts to become finally interesting. So this whole part, I explained it, how it worked, and you definitely get a feeling for what the ideas behind the algorithm, how it worked. But now you see the algorithm, well, basically fail. So that's why it is more interesting. We have to make this work. So now we have a cubic fit through these two data points, and we are looking for a maximum on the left side, and that maximum is over here. While we are looking for this maximum, yes, this one. But if you just look at this part here, and then the cubic looks as if it is going up and up and up, and then maximum is here. So we jump here, boing. Now you see here in the blue line what the drop is between what we predicted and where it actually is. So I think that this distance here must somehow be an indication that our previous cubic was a failure. But it was not really a good match. Nevertheless, now we have a cubic fit between 14 and 15, and it's still possible that the actual function is going like this, because that matches both 14 and, well, almost 4 and 15. So there's no reason whatsoever not to jump here, because it could be the actual function. And then we do that, and it stops, and unfortunately, because I want to talk a little bit more about it. So I'm going to go back until we are there again. Okay, I went one too far. Should not jump to be. So this is the last point. Yeah, so we go here and then we find this point, and this is again a big deviation. So it's again like, that was bad. And now comes into play the question how to make this algorithm work. And I think that the correct way to continue here is to realize that this cubic is just not a good fit for the actual function. And you can see that from this drop, also from this drop. And because of that, we should hang on to this point. So I don't want to fit between 15 and 16. It would be end up here. I want to fit between 16 and 14. And then we'll have something like this, I guess. Which is a good fit. Finally we get a good fit. Then we jump to under maximum and then we're already here. And maybe then we say, oh, no, that was a good prediction. And we can just continue and we find this maximum as we did before. Well, yeah, that was it. You said in private chat to me, I think I can't help you. But if now I explained it like this, I hope that you have a reasonable idea of how the algorithm works. Apart from the last thing that doesn't work yet, so I still have to write it. But the general idea is you have 2 points, fit a cubic, jump to the correct minimum or maximum, depending on if you want to go left or right, depending on if you're looking for a minimum or a maximum. We just depend on where you came from. What we really want is just go from a minimum to a maximum to a minimum to a maximum to a minimum to a maximum to a minimum, alternating. That's what we really want. And one of the problems is that you might jump too far. And then you don't have to look at the code, you don't have to work out the complete mathematics for it. It's just the general idea, you know, what to do. It seems to me that I maybe already said it, so this distance here somehow should tell me that this point is not good. Because, well, we jumped too far, let's put it that way. And we want to find this point, so yeah, sorry, it's clear that we need a cubic that's like this, that's what we need. So we need this point together with a point that is much closer. So one thing I could do, for example, is say, if you see this drop, just throw 15 away completely and just half the jump distance. So pretend that 15 never happened and then not jump this distance, but only jump half of it. And then we would end up there. And if then the prediction is still wrong, well, actually the prediction, then we don't have a prediction. So that doesn't work. Yeah, that doesn't work. You can't just half it and then do the same thing. Then we would have to make a fit between this and that, in which case it would fit reasonably. But of course that's not necessarily going to be the case. Let's say we jumped even much further. Could be, you know, you're a little bit tuning here and we would not jump here, we would jump even further. And then halving, if you then half the distance, you would come here. But now we wouldn't have this drop. We would just have halved the distance. So we would only know that we have 15 here. How do you know then that it is wrong? You would just have this curve and you would not know that this is not a match. Then you would have to jump there anyway, of course, and then see that then you drop. So I would have a fit and then see that it doesn't match and then half that and then have a fit and not know that it's just like alternating. The other cubic, you would know that the previous one was not a good fit. So I don't know, that doesn't feel like a good thing. So it's probably better to say this is not a fit and then jump to this, have a new fit, so this one, and then jump to the maximum of that. Then you have every time this drop. So we have the drop here, and then use this fit, and you have the drop from here to there, and you have another fit, and then we jump to that maximum, and maybe again a drop that shows that even that one is not correct. until we finally have one that is a good prediction, and then we can let go of 14. Does that seem like a good idea? Or does this help you in understanding the algorithm? Ah, great, great. Yeah, the picture says way more than the words. If you just look at the code, I can completely understand that you would say, oh my god, I have no idea what's happening here. You need this graphical feedback. That's the only way that you can have any feeling for what's really going on. And with that, then it might be a little bit easier to understand the code as well. I'm going to bed, so what I will do is I'll just commit everything I have right now, so you have the exact same code then. And then if you want, you can do this yourself and maybe even look at the code, step through the code, or read the debug output or something, so you could you understand even more. What is being executed, how the code works such that we get these points. But yeah, I mean, I would totally agree with you that it's very complex, the code itself. It's ridiculous. This seems way more simpler than I would say it actually is if you look at the code, because there's so many exceptions, so many special cases. So what I have is a little formula for getting to the next W value. So as you know, the kernel of the running the algorithm is this. So it's just these two lines. So if you can just call this a line, you would just recursively call the parenthesis operator on the algorithm object. This GDA is just an algorithm object, and that has an operator parenthesis where we pass W and LW and a derivative of W. So the three points that make up a sample. And we keep calling that. Every time it returns, the W value has been updated. So the algorithm gets a new sample, namely the W value and the value of the loss function, basically, or whatever the function that we currently want to find a global minimum of and the derivative thereof. And then it figures out, using all the previous calls or the whole history, what would be a good W value, a good next W value to get these values for. And this is passed as a reference, so when this function returns and it returns true, then W was updated, and you just immediately call it again, and then you give it these values for that W value. So W is being changed, that is the horizontal direction. Every time this returns, we got to go to a new point with a new W value. And the algorithm finds out the step that you want to take from one W value to the next. Great, man, great. Yeah, I really have joy from it, that I'm not doing this alone. So I really like it that you have this interest and you look at it. Now, so every time we call this function, it has to decide what the next W value is. And there is a lot of special cases, basically. And each special case has its own little formula, which none of those formulas are really difficult. It's really adding the scale, subtracting the scale. I wouldn't worry about the scale. I figured that out. It's kind of, you know, if you don't know what to do, but you want to go in a certain direction, what shall I add? Well, just add the scale. And that's okay then. Or we have a cubic fit, or we have a fourth degree polynomial fit, and then we jump to an extreme. And then that's a W value. But how exactly is it decided that which formula we take? Do we jump to the minimum of a cubic fit? Do we jump to the maximum of a cubic fit? Do we jump to the minimum of a fourth degree polynomial fit? Do we just add scale? Etc. etc. That is decided basically by, let's see if we can find that back. I thought I would quickly see this in history, but no, of course not. Yeah, one of these. Now these are all for when you have a single sample. And the testsuite already tests each of these things. So it's not really interesting to look at the function handle single sample. You have just one sample, which then has all these special cases because they work. They are already part of the testsuite. They are continuously tested. So you can kind of ignore these. They work, okay? So we have to concentrate on these algorithms. You can see they're all different. We have an algorithm for extra sample. So I can explain all of them. Why not? I'll just start at the top. If we found a local minimum, if we found a local extreme, so either we really are in a minimum or a maximum, then I want to fit a fourth degree polynomial, but we need 3 points. If at that moment we have only 2 points, then we do this. It requests then an extra sample in the neighborhood of the local extreme, such that after that we have 3 points. The best zero is a jump to the best zero of the fourth degree polynomial fit. So we found an extreme, we fit a fourth degree polynomial through 3 points that we found. And then the derivative of that fourth degree polynomial has 3 zeros, of course, but 1 zero it drops out because that belongs to the local extreme that we just found. So there are only 2 zeros of the derivative that are interesting, and then one of them can be the best. If we jump to that, and this is so jumping to actually an extreme, a local extreme of the fourth degree polynomial. Past extreme, no zeros, that is done. That's actually a good question. I think the no zeros means that the fourth degree polynomial fit does not have any other local extremes. It could be, it can look like this if you can see my mouse. So like, no, again, go down, and then you have a local extreme here, and then a local extreme here, and then a local extreme here, and then so then we have 3 of them. But it can also be just, I don't know, x to the power 4, like zip, or zip. Just one minimum, and then that one belongs to the local extreme that we found, and then we don't have anything to jump to. And I guess that past extreme, then yeah. I guess it's the extreme and then plus a little bit, but keep going is almost the same thing. Sorry, you have to look at the code of the differences. But these, the no zeros definitely refer to the fact that there is no zero to jump to. No extreme to jump to, actually, of the 4th degree polynomial fit. Downhill means that there is no better way than just do the normal gradient descent thing. It could be even learning rate times minus the derivative, so the normal gradient descent. Although very early I determined something called a small step, which is not really a learning rate times the derivative, because I found that kind of, stupid. So I replaced that step distance by something called small step, which is, I think, a better step to make. Could be that as well. You would have to look at it, what it exactly is doing. And then the first time we jump to an extreme of a cubic, that would be this one. And the jump after that 2 cubics is this one. Keep going is again that we can't jump. Just we don't know any extreme. There is no extreme, but we want to go in a certain direction. So then we just add a scale. And by adding the scale, 2 things can happen. Either that the new point is still a good fit for the old approximation, and then the scale grows. So as long as that is so say you have a certain approximation. Let's say the approximation is even closer to parabola, so I can draw it easily. Parabola. The scale is then from the vertex horizontally to the last point. That's still a good fit. If then you add that same distance again, and that new point is still on the parabola, then the scale is doubled. So then you add that scale again, then the distance is twice as big. If that's still a fit, then the scale is grown again. So the scale doubles until you find finally a point. You add the scale again and again and again until some point it does not fit anymore. So then that's called that it is disconnected, and then we start over. That means we start a new approximation. So then you have only a single sample. So then the first one uses this algorithm, and then the next one just uses the last two samples plus a new approximation that is fitted through those 2 points, and then you have this one again, the initial find extreme jump. This one means if we are we are going left, say we're going right, and we find a maximum. We start, and the first thing we find is a maximum, and then we find a minimum, and then we are bored at some point. For example, after that it only goes up and up and up. Then we can normally, after an abort, we jump to the best minimum, which could be this minimum. and then start explore in the other direction. But doing that, maybe I should just pick a graph. I don't know how visible the mouse movements are of me. So I suppose we find this one first. You see my mouse, right? So we find this one first. And then we find this one. And then we go on in that direction. And then here we abort, because this is not lower as that one. Then what normally after an abort, so we abort going to the right. Normally that means that we jump back to the best found minimum and then go to the opposite direction. However, we already know the maximum, right? First we found the maximum and then this minimum and then the maximum, etc. So it doesn't make any sense to jump back here and then start searching for the maximum again. So what I do then is I go here and I see that we already have a known maximum extreme as a neighbor. This one is already known. That is stored as a link in this local extreme, which is local extreme object. So that would be holy liebe kaput. Okay, I give up. That would be this one. So we abort, jump to the best minimum, and then go to the neighbor, because that in the opposite direction, because that neighbor already exists. And then the last one is the thing without the neighbor. So we just abort a certain direction, then we jump to the best minimum, and we go in the opposite direction without jumping to the neighbor of the best minimum, because that doesn't exist yet, or wasn't explored yet. And these are all the different algorithms that exist. All these that I needed so far. I think it's time for me to go to bed. It's midnight. Engineer, yeah, it's on GitHub as well. I used to have an FAQ with this. I don't think my font is on there. I use a Deja Vu Saw Mono 16 point, but 16 point is only because I'm on YouTube. Normally I use less. Let's see what I normally use. Normally I use this, which is actually hack 12 points. So yeah, either the previous one, the Deja Vu 16 points is larger, or the hack 12 points. And then for the colors, you would have to look on GitHub. I'll give you the link, even though I want to go to bed. Stories. You need a true color. What is it called? Terminal. And you need Vim or new Vim or whatever. Vim or new Vim. So if you're on Windows, what are you doing here? Damn it. Looking at my Windows editor and thinking it looks good. Okay, I'm going to stop streaming. So good night. Talk to you tomorrow, Gonis.